this is lecture 24. We will now conclude our discussion on entropy-related properties of submodular functions and quickly do submodular information functions and also look at submodular function maximization. So briefly recap that we talked about information functions beginning with the definition of entropy. And then we also looked at a notion of the information gain, right? So h of A union E minus h of xa, that's a gain you get, right? So what about that? So there are entropy, mutual information, information gain, conditional entropy to add to this conditional entropy. Then we also defined the notion of KL divergence. And so on, right? So yeah, beginning with conditional entropy. Yeah. This one. Thanks. Yeah. Okay, and this one as well. Yeah, this is a minus. Mutual information should be fine. Mutual information is fine. Sorry? There's a minus here. Oh, sorry, that's not required. Yeah, there's already an edge here. That's fine. This was all fine. I think only the previous slide there was a minus missing. So we defined mutual information as well, which is kind of how much is the information that X and Y share between each other. And the best visualization of mutual information would be here. This figure will be sticking around for most of the while. So you know you have h of x given y on the left hand side, h of y given x on the right hand side, and this intersection is the I of x comma y, the mutual information. I mean, this is just representative. And h of x comma y is this entire thing, a joint entropy. Is that clear? So what is in words, ix comma y is a reduction in the uncertainty of x due to the knowledge of y, but it's symmetric. It's also a reduction in the uncertainty of y due to the knowledge of x. That's why you can view this as the intersection, roughly. KL divergence again is asymmetric. It's not symmetric. It's basically the distance between two probability mass functions, again computed as expectation. So d of p with respect to q is the expectation of log of p divided by q with respect to p. So the expectation is with respect to p. Okay. Right. On the other hand, if you write d of q given with respect to p, then you'll have exactly the opposite, qx log of qx divided by x. So it's asymmetric in that sense. However, there's an information inequality which says that d of p with respect to q is always positive, not non-negative, and equality holds only if p and q are exactly the same distribution. In that sense, there's a bit of symmetry. Modulo this, they are asymmetric. Is that okay? So this is again recap, right? So we proved this. I'm not going to go over this again, but recap the proof. It's for information inequality. Right? This is the information inequality. So without further ado, let's move to the homework problem. Homework problem was to complete the proof of submodularity of H, right? Where did we leave ourselves with? We said, well, I of x comma y can be also viewed as a KL divergence Okay, then again a bracket is missing. KL divergence between the joint distribution of P, a joint distribution of X and Y, and the independent distribution of X and Y. The left hand side is the independent distribution of X and Y, or distribution X and Y under independence. And what we have on the left hand side is a joint distribution. And we know that information inequality tells us that this will be always greater than or equal to 0. Okay, and in fact, the equality holds if and only if X and Y are independent. The joint is the product of the marginals. So therefore, from this, we know that mutual information between X and Y is always greater than or equal to 0, which is the same as removing the dependence of X, or the part conditioning on Y, what gives information you get about X. If you remove that from X, that's the intuitive verbal definition of mutual information that we saw earlier. Okay, so this is interesting. So now basically what is this saying? It's saying that h of X given Y is less than or equal to h of X with equality only if X and Y are independent. Another way of looking at this as h of X given Y is less than or equal to h of X given Y union, h of X given empty set. So this you could view h of X as h of X given the empty set. Now how will you extend this to get the proof of submodularity of H? Any suggestions? Can this view help you? H of X given Y is like the gain, right? Conditional gain. Conditional entropy. Any thoughts? Y as a singleton. Okay. What if I say instead of empty set I have a Y prime which is a subset of Y. See, note that empty set it is a subset of Y. What if you had a Y prime which was a subset of Y? So how will I extend this to that case? What would that be? H of X given what is less than or equal to H of X given what? Whatever. If Y dash is small, it's actually covering less of X, and therefore again you get by adding more to Y dash to get Y, right? The marginal gain you get through X is going to diminish, diminishing returns. So you have to basically extend this proof. So I'm not going to do that in the class. You'll have to now define. You'll have to define something like conditional divergence. So we had d of px comma y from d of px y. Imagine now you condition the KL divergence. Okay. Okay. So above proof methodology can be generalized to prove that h of x given y prime is minus h of x given y is greater than or equal to 0 whenever y prime is subset of y. And I mean the inequality will hold only if the conditional distributions are the same given y prime and given y. Okay, again this is extension. This is basically extended from probability of x given y is probability of x, which is the same as saying that they are mutually independent, right? Okay. Is that fine? It's just lot more notations, but um, hint could require no, like we had this inequality test, right? What was it called? You see this information inequality. Sorry, I forgot the name. Yeah, information inequality. On conditional K divergence. So it's a little more involved, which we will not get. But I think you got the proof methodology of it. Okay. Okay, it's clear now. So we have basically proved that entropy is submodular. But we'll see a lot more properties now. Discrete entropy, we had made no assumptions other than the fact that it's discrete entropy. Okay, so this is again the pictorial depiction. Now, what if I look at this mutual information I comma x? So, I mean, I defined this I comma x, right? I used I comma x as a tool to prove the submodularity of entropy itself. But what about the submodularity of I itself? Is I submodular? Now we can ask a whole bunch of questions. Okay, so let me ask these questions before I go to the next slide. Otherwise, we'll be overwhelmed. So questions. What about submodularity of I? Now, moment you say submodularity of I, you have to ask, viewed as a function of what? Viewed as a function of x comma y, viewed as a function of y, viewed as a function of x. Obviously, it's symmetric, but viewed as a function of both, or one of them fixed, the other moving, right? Viewed as function of both or just x slash y, right? I could also ask, what about submodularity or properties? I mean, submodularity and other properties of, say, h of x given y, the conditional entropy. Okay, so yeah, I think we should be very clear. It's not just submodularity and other properties. Okay. Okay, so let's try and answer these questions next. What do you think? What is your view? Do you think all these will be submodular? Any opinions? Let's start with information gain. So note the definition a little carefully. You got to count information gain, mutual information we had. Information gain is nothing but mutual information viewed as a function of one set of random variables. Okay. So this is information gain is mutual information viewed as a function of the first set of arguments. Okay, and now, so you have x comma y. What is the, if I remove the y conditioned on x from h of y, then basically the part that is mutually informative is there, but viewed as a function of a. So for example, if I'm adding features, let's say y is a class label, right? So let's say it'll be easy to illustrate using, say, let's say y is class in a classifier, and x is features. X1 is one feature, x2 is another feature, x3 another feature. In fact, I can have a subset of features also. Right? XA is a subset of features. So let's say this is XA, a subset of features. So I'm trying to see, well, how much is that XA informative viewed as a function of A? Y is kind of fixed. I don't want to keep changing the classes, obviously. I don't want to say information of one set of features with respect to class 1 and another set of features with respect to class 2. Makes no sense, right? So this is XA. Okay, so this is mutual information pivoted on the class. Think of it as okay. So now, so we're still looking at this mutual, this area. We're still looking at this area only. So let me do a different color. Right, so it's still looking at this bonding here with respect to the class. Now it turns out that FA is not always submodular. Okay, and we'll show one special case when it's just submodular. The reason FA is not submodular, very verbally explained, is that even if you fix the class Y, the features themselves may communicate. For example, let's say one feature is height measured in inches, right? Other feature is height measured in centimeters. Okay, so are they really independent? I mean, the features are not independent, right? So there could be a lot of correlation between the features. But if given the class label, these features are independent. If I tell you that it's a particular class and the features are designed such that they are independent of each other, then you can claim that they are this information gain is submodular. Okay, so FA is not always submodular. I'm just going to give a very they might be dependent even given the class. So for example, height of a person in centimeters, height of a person in inches. Are they independent given whether a person is underweight or not? Right? E.g., x1 is height in centimeters, x2 is height in inches. Probability of x1 comma x2 given y, whatever underweight, is it equal to probability of x1 given underweight into probability of x2 given underweight? No. They're right. So at least they should be conditionally independent given y. So I'll have to move this description now. Okay. So I'm getting call urgently. Um, okay. So what you could do is, however, if they are independent, so you all have heard of knife-based classifier, right? The features XA are independent of feature XB given the class label. If that happens, then let's see what the decomposition is. F of A is I of Y comma XA, which is H of XA minus H of XA given Y. Okay, this should be all familiar with you. This is exactly reproducing the definition. Okay, and this turns out to be H of XA. Now, if they are conditionally independent, then this is an interesting part. H of XA given Y is the same as summation over all the A's indices. Like, let's say X1, X2, X3, X4, X5. So this decomposes. Why? Because we know naive-Bayes assumption will mean that probability of XA given Y is product over A in A of the probability of X small a given Y. Okay, so then you can easily show that this equality holds, right? Entropy is log of involves the law of probability, so you can show this easily. Okay, so information gain can be submodular under this assumption. Why? Now what happens is you have a submodular function minus a modular function. This is the first component is submodular. You already know. The second component is now modular. And it's submodular minus modular, submodular minus modular, which will be submodular. Is that okay? However, what you often do is you boldly go ahead and say, well, even without naive-Bayes, let me try and minimize this. Why? Because actually it's a difference of two submodular functions. So it's a difference of submodular functions. H of XA given Y is also submodular. It's after all no, fixed Y for a fixed Y. Okay. Because it's just conditional distribution, right? Conditional entropy is like same as entropy where you're conditioning on one Y. Okay, so now given this difference of submodular functions, there are ways of optimizing this as well. Okay, so the way there is an entire set of methods called majorization minimization. Could be optimized using. So we basically you alternate, right? You try and if you want to maximize, right? You would say maximize the first component and then minimize the second component. Majorization. Minimization. But anyways, that's just for your knowledge. This kind of difference, right? So what you'll do is you'll alternate between the first component, which you'll majorize. You'll consider majorizing that, and the second component, minimize that in case you want to maximize the whole thing. Okay, and the other possibility is even if it's not conditionally independent, you can make a submodular approximation. So what you do is, okay, you don't do h of xa minus h of xa given y, but you approximate this whole thing, the second component. They're not independent, but let me just make a naive assumption. You know that naive is an assumption after all, right? So many classifiers with by which so many data sets where naive doesn't hold, you still learn, and it works pretty well, right? At least in the pre-deep learning era, it was one of the most formidable baselines. So you could do that. You could just go ahead and say, okay, I'm going to anyways make that assumption, and that's a some modular approximation. Is that okay? Is this clear? I mean, it'd be nice to just write down these basic expressions as we proceed. So what have we seen so far? Just recapping. We've seen that mutual information viewed as a function of one of the arguments, x, is submodular when the components of x are conditionally independent given the other set of random variables y. But irrespective of this assumption, sometimes you can make a submodular approximation and make that naive-based assumption via the naive-based assumption. However, the submodularity of entropy doesn't require any of these assumptions. Entropy is always submodular. Discrete entropy is always submodular. Okay, so we have some monotone submodular functions. Some of these we have seen, and we have enough motivation now. Non-monotone submodular, graph cut, mutual information. Okay, by the way, mutual information is submodular under those assumptions, but it's not monotone. Entropy, by the way, is monotone. I think we saw that already. Entropy is monotone. It's submodular, but as you keep increasing the size of the set, the entropy cannot decrease. It only increases. I think we have seen a proof that one of these statements we had already seen. So proving the statement. So this is a picture so far of what we have seen. Now we're going to do the following. So again, we look at this bird's eye view. We have submodular functions, monotone submodular, and then supermodular functions, and then a big class, a big subset of submodular functions has to do with entropy. But now we are going to look at using the formulations around the entropy, mutual information gain. What if we use that for other submodular functions? Okay, where do they fit? Okay, where do other submodular functions or where does application of information gain, etc., which we'll see, right? Information gain, conditional entropy, etc., apply fall when applied to other submodular functions. When I say other than entropy. Okay, so that's a curious thing. I mean, so just to give you an idea, right? If you have monotone submodular functions, if you so while entropy was here, moment I applied information gain, so information gain basically based on the entropy was straddling between monotone and non-monotone, right? Oh, sorry, it was straddling between submodular and non-submodular. Where was that? This is somewhere here, right? So it probably brought me obviously non-monotone. This is information gain. So then we are curious what happens when we apply the same concepts to other submodular functions. Is this clear? So this is the application. Application of information gain, for example. This is where you are. Okay, so let's see that. So we'll now define these information measures, which is related again to your assignment, your second assignment, or application related to your assignment. Okay, so we'll define that and then give examples. Okay, so recall all these information theoretic concepts once more, right? Which is entropy on discrete random variables, mutual information. We've seen that basically looking at h of xa plus h of xb minus the h of x union a. Basically, if you are dealing with set functions, this would be intersection, but it's more entropy. It's not just set. So it's like this view. This is I of x a comma b, and here you have a, here you have b. To keep this approximate image in mind. And then conditional entropy was what? The one on the right hand side, right? This part is a conditional entropy. H of x a given x b, or x b given x a, and so on, right? And this would be h of x a given x b. But now you can do fancier things. You can say, okay, conditional entropy, I can do conditional mutual information as well. So what does this entail? We're saying I'm saying that I can do a h of xa comma xb given xc. Okay, so just to be, I'll do the same thing as what I did here above, and now I'll bring a conditioning on xc, like we did conditioning on xb. So I can have these combinations. Basically, you're saying also information between information in the intersection of A and B, given that C is already known. So you've done probability distributions, conditional distributions. Think of it, but in a discrete sense, because now you're talking about indices on random variables. So that's why it's a discrete optimization setting. Is it clear? Okay, so why is this so interesting? Why is entropy suddenly becoming so exciting for us? Well, it looks like when Shannon defined, the inequalities for entropy, he did not know about submodularity. Sometimes there are different communities, whether it's graphical models or whether it's entropy. Many of these evolved in different communities in different ways. They never spoke to each other. So Shannon had these three properties. We refer to f of phi equals 0. That is the function entropy on an empty set being 0. Entropy being monotone. F of a greater than or equal to f of b if a is superset of b. And he had a slightly different notion of submodularity, or different word for submodularity, called it two alternative. And now you can see, well, this is related to the second definition of submodularity, or second equivalent property of submodularity. Two alternative is the second equivalent definition of submodularity, right? Which is f of a plus f of b. That alternative is greater than or equal to f of the union plus f of intersection. I mean, you can see this in the same, right? So f of a plus f of b, f of a plus f of b is greater than or equal to f of a union B plus the f of A intersection B, which ordinarily would have said equality if we were just looking at the cardinality, modular functions. Okay. So that's the reason there's such a strong bonding between entropy and submodular functions. Now, property 3 implies non-negativity of mutual information. Why? In fact, it implies non-negativity of mutual information and conditional mutual information both. So I'm going to leave this as homework for you. You have to think about it. Okay. And another homework I'm going to leave for you is properties 1 and 2 together imply non-negativity of entropy and conditional entropy. Okay, think about this. Why these properties hold? So mutual information or conditional mutual information, which is basically very closely related to mutual information, that's non-negative. And properties 1 and 2, they together imply the non-negativity of entropy and conditional entropy. This is not very difficult. Okay. Should be able to reason it out easily. So basically, entropy, conditional entropy, mutual information, conditional mutual information, all of these are non-negative. That's a very nice thing to know, right? But there is another interesting thing. There's one might be wondering, well, are there other functions that behave like entropy? Right? So there seem to be polymetroid functions. See, submodular functions in general need not be monotone. They need not be, normalized. And then the submodular function on empty set need not be zero. Okay, so think of a huge set called submodular, just submodular functions. And a part of that is what a subset of that is what is now being talked about as polymetroid functions. And I'll tell you why this matroid, right? It's related to matrix. Okay, so I haven't really included those slides, but let me just for a minute I'll give this example. So matrices and their ranks, right? So what is the rank of a matrix? Let's say this is A. What is the rank of A? Just give me a verbal definition. What is the rank of A? Okay. Dimension of column space. The maximum number of independent columns. Right? Now, is this maximum number of independent columns normalized? If I give you 0 columns, what is the rank? 0. Okay, so let's just write down its properties. Okay, so rank of empty matrix. I mean, if I basically rank of, I mean, not just matrix, right? Rank of, I think better to say is rank of columns, a subset of columns, right? Set of columns. This is the maximum number of independent columns in that set, right? So rank of empty set is going to be 0. What if what about monotonicity? Is rank what do you think? If I keep adding columns to the argument of rank, will the rank shrink ever? Rank won't shrink, right? Rank function is monotone. Very simple. Submodularity. So if I give you, think of the other definition of submodularity, right? If I give you a matrix, and now to this matrix A, I add an additional column. It is an additional column I'm adding. Let's call it E. If I add E to A, as against adding E to a subset of A or a superset of A, so let's say I have a superset of A, which is called okay, this is B. Okay, so B is a superset of A. So what can I talk about? Rank of A augmented with E minus the rank of A. Like how much is the value E is bringing to A as against say the rank of B, which is a superset of A, in conjunction with E, augmented with E. So this, sorry, this is not. I don't know what to say. Comma. Let me just put a comma. That's easy. It's not condition. Okay. Minus the rank of B. What do you think this property will be? Greater than equal to, right? Because you can imagine that E, if I add a column E to B, I mean the the set of independent columns may not necessarily grow, right? The additional set of independent columns, not the set. Additional set of independent columns may remain the same, but cannot certainly grow, right? So there's more value that E is potentially going to add to A than it's going to add to B. So you see, this is the reason that you see this matroid. The matroid structure is a generalization of what we have in matrix. So we'll actually not go more than that as far as matroid is concerned right now. Okay, so it turns out that any such function which satisfies these three properties. Okay, so I'm going to just highlight these three properties again. So these three properties any such function is called a polymatroid function. Which is normalized, which is monotone, and which is submodular. And it turns out that polymatroid functions generalize entropy. Okay, so there are. Okay, so now question is, okay, let me now we have brought up another dimension, which is entropy. Where does entropy really fit in the scheme of these things? Okay, so this is entropy. Okay, so the question is entropy this entire set? Where is entropy? Is it a subset here? Is it a subset here like this? Or does it coincide with the entire polymetroid functions? What do you think? Subset? You think it's a subset? Let's, yeah, it turns out. Okay, so, sorry, that will come later. Okay, this is, so you're right. So polymetroid functions strictly generalize entropy. So indeed, that picture I showed you earlier, that I should have changed the order of the slides. Anyway. This actually holds. Okay, this is the right picture. You're correct. The submodular functions, you have entropy, and you have polymetroid functions, which are subset of submodular functions, but a superset of entropy functions. Okay, and there is a reason. Okay, some of these I'm a little fast on that. So it turns out that this holds for all convex combinations of entropic functions, and it's not that submodular information measures will not satisfy this. In fact, even polymetroid functions need not satisfy this. So this is inequality. This is very much. This is equality. I'm sorry. This is inequality only. This is this inequality. Okay. This is very characteristic of the submodular information functions. I'm sorry. This is characteristic of entropy. That so entropy functions need to satisfy this inequality, which polymetroid functions are not obliged to. Submodular functions are not obliged to. Right. So there's a constraint which is only for the subset, not for the entire set. This is clear. And that's basically looking at given 4 random variables. So it's looking at 4 combinations of 4 random variables for which you have certain inequality x of I of x3 comma x4 minus I of x3 x4 given x1 and so on. We'll not spend more time on this right now. It's a strict subset. Sorry? I'm going to do that. So I'm talking about submodular information measures. Okay. So now, what we are saying is now we are going to generalize our observations on entropy to submodular functions. All our mutual information, K divergence, information gain, conditional entropy, all of that will generalize. Okay. So here are our definitions. F is the information. It's called the information. What is submodular mutual information? It's exactly the same as mutual information, but you have replaced the submodular function with F. Okay, that's the only thing you have done. That's what we mean by submodular mutual information. In general, that's how we get submodular information functions. In mutual information, replace entropy with any submodular function. Okay, so you have seen this. If you had H, if F for H, you'll get mutual information, right? Setting F as H, you get regular mutual information. Likewise, you can define a conditional gain. Gain of adding B to A is the gain of A union B minus the function of or information function of A union B minus the information function on B. So same thing. Everything is now going to be, now we just have F here. Okay, you have F in the superscript. Here, by convention, we have F of A given B. And like before, you can have combinations of the two. You can have F of A given C plus F of B given C minus F of the F of A union B given C. That is the mutual information between A and submodular mutual information between A and B given C. Is this clear? So this is what we mean by submodular mutual information. Just replace entropy with submodular that gives you submodular information functions, including mutual information. Okay, so submodular information measures, the notion is clear from the name. But for submodular conditional gain, there's a gain in information when you add set A to set B. Mutual information is a joint information between sets A and B based on F. And we'll see for each of those functions like set cover, representation, what each of these means. We'll see some samples. Independence. We can also talk about independence, like we talk about entropy, h of a x comma y is h of x plus h of y if x and y are independent. We can have a similar notion of independence modulo the submodular function and not entropy. So the notion of independence is maximally different sets A and B, but through the lens of F. F is basically the lens. Okay. And this is exactly what I was saying. The submodular information functions are also a strict superset of entropic information functions. So entropy is a strict subset of submodular functions, strict subset of polymetroid functions. And submodular information functions are also strict superset of entropic information functions. All that entropic information that has to offer, right? So now we are just a kind of gone ahead from from entropic information, which includes all these gain functions, mutual information, scale divergence if you want, and so on. And now you're going to submodular information. In fact, there exist polymetroid functions, metroid rank functions which do not satisfy the inequality above. Okay, just as an aside, so some of these slides I'm going to go a little fast and then again slow down when we look at very specific examples. These are both properties. So as I said, you can have a notion of independence in the case of entropy, right? Mutual information between A and B, if now is 0 with respect to F, then we say that the two sets are independent with respect to F. You remember when was the mutual information between X and Y 0? Right? Recall that I x comma y was 0 if and only if X was independent of Y, right? Because it's because ixy could also have been written as I of X minus I of X given Y, right? So if they're independent, then I of X given Y is I of X. So it becomes 0. Okay. So you can also talk about conditional independence. You can say A and B are conditionally independent given C with respect to the lens of the F. If IF of A, B given C is 0. These are like notions of pairwise independence. Okay. You can now also talk about multi-set submodular information, something we are not going to build upon. This is going to be a little kind of breezy, and I would say this is like really extra optional. No, if you're very curious about it. But let me give you an idea what these are doing. So if you're given multiple sets now, you can have a notion of submodular total correlation. How much are these sets correlated? Right. So it's generalizing the notion of mutual information. Mutual information I only looked at IA plus IB minus of I of A intersection B. Sorry, I of A union B, right? So recall, this is generalizing. So you had I of A comma B is I of A plus I of B minus of the I of A union B, right? Now what you're saying is, well, I generalize it and say if I had an I of AI, what do I do? Right? A1 to AK. Then I'll say, well, I'll do the summation over I equals 1 to K of I of AI minus 1. So this first part is clear. The first generalization is clear. And that's exactly what we have here. But the second part, we are saying, well, the generalization of the second part will also be that I took a union over all the AIs. Okay, that's the second part. Okay, now I can do this on any submodular function F. So this is total correlation, but there is another related notion of multiset mutual information. Okay, what here you do is basically, so the inclusion exclusion, right? So what is this doing? So this is basically implementing inclusion exclusion. So what is it doing here? It's saying depends on the size of t. If size is even, then you'll have positive sign, right? So let's kind of write it down. What might it look like? So there's a minus outside, sorry. Okay. So initially you'll have, this will be basically what? Summation over I equals 1 to K of I A I. So this will be the same as above. Exactly the same as above. The first, right? If you have a single element, there will be a negative here and one more negative here, right? And so that part is same. But now instead of jumping to a union directly, okay, also a final component will remain this. I mean, something similar to this. You'll have the part in green, but now you're growing it in stages. You're saying the second component will be minus for all possible I1 comma I2. You'll have I of AI1 comma AI2. So initially you thought they were all independent, but now you're trying to reconcile. No, what if there's some dependence? But then I've over captured dependence between the AIs. So I want to now do course correction and say, well, let me add back what I additional unnecessarily subtracted. So it's in inclusion exclusion. So you say AI1, okay, so now it's the same thing. So it's I hope it's clear, right? I1, I2, I3 of AI1, AI2, AI3, and so on. Okay, so you can kind of now imagine this is another definition. Instead of jumping from just, it's adding these intermediate terms here. Adding all these intermediate terms instead of the green part. So you can think of this green. So you've probably done pairwise independence, right? So all this has analogies and or the analogs in your independence of random variables as well. Okay. Okay, so you can actually illustrate this pictorially. F of A given B, we have done this before. F of A given B, you would look at this region, right? This region. So it's going to be a little tricky to highlight all of this. So I'm going to this is F of A given B. but which is basically what? F of A union B minus F of B. F of B given A, likewise I can look at it, but F of A intersection B, mutual information between A and B, we had likened that to this intersection region, right? So A given B was like trying to exclude the part of B. Here I'm looking at what is common between the two. But now you can do the same thing for K equals 3. That's the second part here. So you can look at IF of A given B union C. So now I can look at which two sets are conditioning on. And like if it was just A given B, I would have just taken this entire set, right? Had it been A given B, maybe there's no A given B here, right? Yeah, there's no, I mean, that's like this, A given B is this. But if I were to look at A given B union C, then this would be the region I'm talking about. Okay, so I hope you get an idea. If you're looking at A comma B given C, okay, let's look at just one more example. A comma B, that's a mutual information between A and B, or let's look at B and C that way. Between B and C, right, this is the region between B and C, but given A. So it's B and C. Ordinarily, this would have been right I of B comma C. But now, since I want to condition on A, what am I looking at? I only look at this part. This is B comma C given A. Did you get these two examples? I think others will follow. All the others are basically variants of this. Are these two examples clear? Okay. Okay, so I would like you to know, maybe you would be asked some question like this. Just map it intuitively. You should know, you should understand what conditioning does, what intersection does. So try and identify. So homework, I mean, I would suggest homework. Try and identify regions and corresponding information functions. So when I say information functions, it need not be mutual information. It could be any of these. Right? So you might be told, okay, what about this region? What does this capture? Okay. So now let's look at examples of submodular, of information functions. Now, when I say information functions, we are really talking about submodular information functions. Okay, so modular functions. Simplest. I just have three different things, right? I have an ice cream, I have some pineapple, I have some juice. So f of a for modular functions is sum of the individual elements. But moment I condition f of a given b, what does it mean? It's a set difference. I look at the weight of all the elements in A which are not in B. Let's just write simple verbal descriptions here, okay? It's sum of weight of all elements which are in A and not in B. What is IF? Sum of weights of all elements which are both in A and B. Right? I mean, I can just extend the same thing and say the last one, the second last one of all elements which are in all AIs. So modular is very simple to understand. You can actually expand it, right? And what is independence? Basically, he's saying I of a comma b is 0 means there's no weight associated with the elements. Intersection is 0. That's the only way, unless some of the weights are degenerate on 0. Otherwise, the only way you can, if all elements are, I'm just assuming, assuming that all elements have non-zero weights. This is clear? So simplest is entropy, which is modular if the variables are independent. This is the simplest example. But let's look at weighted set cover. Yeah, I'm trying to give some explanation. So read the text a little bit more, and we'll also keep writing as we describe. So gamma will be the elements covered. So let's just recall, right? So if these are the documents, okay, documents, and A is a subset of the document. Okay, A is always going to be a subset of the docs, which are these basically. These are the entire set of docs. Each document is going to cover some words. Okay. So this gamma, I write down the gamma here, okay, and let's call it D1, T2, T3, and so on. So what is gamma of D1? D1 covers dog, bird, beach. And so on, right? So that's what gamma is. So in general, gamma of, now let's look at this, right? So gamma of D1 comma D2 is what? You'll take a union of all the elements covered. So it's dog, it's, oh, did I drop cat? D1 was cat, bird, beach. Oh, I made a mistake. Just type it better. Cat, bird, and beach. Is cat, bird, and beach. Okay, so now if I consider two elements D1 and D2, then looking at cat, bird, beach for D1, but D2 covers dog. Oh, some links are missing. Let me do D3. I think D2 is not fully specified. Let's look at D3. Okay, so what is D1 comma D3's coverage? D3 covers bird again, right? D3 covers some other concept also. So bird will not be repeated twice. It's a union, right? And then you'll have other terms covered by D3. So this union has taken care of a kind of repetitive beach. So that's where the diminishing returns comes, right? Okay. So now what is f of a is the weight of all the elements covered. So for example, in this case, it will be the weight of say cat plus weight of bird plus weight of beach and so on. Correct? Weight of all the elements in that set. A given B. Okay, so now I think I should put a B. So all this was A. Okay, so A was should I just mention? Let's just take A to B. For this entire slide, let's say A is D1, D3, okay? And let's consider a particular B. Actually, we can only take B as D2 because yeah, others are not named. So B is D2. And D2 covers dog as well, right? So f of A given B is what the weight of all the not the documents, but the elements covered by those documents, the words covered by those documents. What will that turn out to be? So now what we'll have to do, weight of those covered by A and not covered by B. Right? So dog, oh dog, nobody covered, is it? Dog D2 did not cover. So I'm a little at loss. So I have to put some more edge here to make sense of this. So let me, yeah, so dog was not covered by anyone else, unfortunately. But let me put this link to bird to make it actually more useful. Okay, yeah, this should be helpful. So this will lead to what? It lead to W of, so I will now have the weight of cat plus weight of beach, but I'll have to subtract I will not have the weight of bird, right? I don't care for the weight of dog because dog never occurred in D1 or D3, right? So what is weighted set cover doing? It's basically, it is basically just some adding the weights of terms, but terms covered through the set elements of A. That's where the submodularity comes. Otherwise, it's the same idea. You understand? So this has no weight of bird. It has no weight of bird because D2 also covers bird. That's the issue. Okay, so mutual information would be what? I mean, it's again now it's becoming very trivial because all you're seeing is coverage measured through, sorry, weights measured through the coverage. Right, so this will be weight of A and B both. Right, so but they should be in both. So what are the terms in both? It's only, I think only bird, right? It's only bird, and so on. And independence is if that is if the coverage of A and B is disjoint. Okay, so you can go back and just write down these simple terms. Right? I mean, the simple explanation. What's happening? Thanks. Okay, and this IF of information A comma B is again weight of terms covered by both A and B, and so on. Okay, so I will not spend as much time on all the others. You can similarly come up with probabilistic coverage. Now the whole notion of coverage is probabilistic. Otherwise, the so this, you look at this Pi of A subtraction from B. So that coverage has to be done in a probabilistic manner. So instead of a gamma, right, you're looking at a probabilistic measure of how A and B are different in the case of A subtraction from B, or how much intersection they have in the case of A comma B. Okay, so all the previous notions of coverage become probabilistic. Okay, so it is slightly trickier, I must say. Facility location. Let's just look at the terms here. So what you'll have in the facility location case is f of a is the most similar element from A for each element I, right? So in fact, we had a name for this. We used to call it GI, right, for a fixed I. Right? Now f of A given B is what? You're saying, well, I'm already given B, so I have to now look at how much similar a point in I is to a point in A, but I want to subtract how similar that point, the max similarity of a point from I to a point in B. Right? So this is like a margin of difference between what the difference between the most similar point in A from the most similar point in B. The max of 0 comma, that is conventional because that's, you can't have negative values. So difference between most similar point in A and most similar point in B with max outside. Okay, so a lot of these you can, if you just write down the verbal descriptions, you'll be able to remember them better. Let's look at this mutual information, what it's doing. It's saying, well, I will find the most similar guy from A, most similar guy from B, and look at what's the min of the two, because it's intersection. Right? Max is if I were probably considering a union, but here you're looking at the min. Min of the most similar values. Since this is about intersection, it should be, you want the point to be similar to both A and B. That's why you're taking min. Okay, and likewise you can do for multiple sets as well, which we'll not get into. So you can now look at penalize sum coverage. This is basically facility location. So if you know, I mean, this is not facility location, graph cut. This is a graph cut. Might recap. In graph cut, we had a lambda here, right? Okay, so if I'm looking at the mutual information now between A and B, is basically the sum of all similarities from A to B. Very intuitive. And here I've already explained what is this. So if A to V slash A, this V, the complement of A, is a graph cut function. So let's actually take an example. Let's say this is A, and this is the A complement or A prime. Right? So in this case, what are we doing? We're looking at the graph cut, the cut of cut involving these edges. So these edges. This is exactly the graphlet function, that is IF. Okay, and independence is if the similarity between the every pair of points in A and B is 0. So then that's when you say that you have independence. Okay, so anyways, you have an assignment where you can try out these functions. Okay, so okay. What are other properties? So we're going to run over these examples. I wanted to spend a little bit more time, but properties, we again want to just understand those properties. Okay, so if f is a polymetroid function, so recall that we had that image. Good to have that image all the time. This image is important. Okay, what happened? So remember that polymetroid functions, generalized entropy, they had monotone, right? Submodular plus monotone plus normalized. It's called normalized, right? So if f is polymetroid, then right, not for any arbitrary submodular function. So with the assumption that f is polymetroid, belongs to this blue region, then f of a given b, all of these are non-negative. So these cannot be said for all submodular functions. I mean, certainly for entropy. These certainly hold for entropy and more. That's what we are trying to say. Entropic information and more. That is for all polymetroid information functions. Okay, and monotonicity. So some of these are monotone, some are not everything. So f of a, obviously, f of a will be monotone if you're dealing with polymetroid functions. Right, so that some of this just holds monotonicity because you're dealing with polymetroid functions. So for example, f of a will hold to be monotone, but f of a given b will also be monotone because in some sense it's just conditioning on b. So it's just a new, think of it as a new distribution, right? A conditioned on b. It's monotone in a. Mutual information is monotone in A for a fixed B. And recall what is mutual information doing? It's saying, I mean, the reason roughly is that if of A given B, comma B, is what is the entropy of A minus the entropy of A given B. Okay, so it's going to be monotone because as you keep adding conditioning, right, as you the gains are going to be as the conditioning part increases. Entropy of A is basically entropy of A given nothing, right? Entropy of A given B. Now you are growing the set. So because of some modularity, there will be diminishing return. So therefore, there is going to be greater than or equal to 0. Not only is greater than 0, it's also as you keep adding the as you keep growing the A, this gap will only increase. Okay, again, we won't have the time to keep doing all the proofs. So if of A comma B given C is monotone in A for a fixed B, for a fixed C, and monotone in B for fixed A and C. So I think the key point to understand in this third statement is the fixed parts. It says fixed C must always be fixed. If you're comparing with respect to A, B should be fixed. For B, A should be fixed. That symmetry is there. But the C part should be fixed always. And then you have upper and lower bounds. F of A is greater than or equal to F of A given B. So we have seen that this is again holding because of the submodularity of F. F of A is greater than or equal to F of A given B. Now the mutual information between A and B is greater than or equal to the submodular function on the intersection. So we already has been trying to intuitively relate mutual information to with the intersection, right? But it turns out that it's slightly different from the function, the submodular function itself on the intersection. Okay, this would be equality if we were dealing with modular functions. This would be equality for modular functions. In fact, both would be equalities. Okay, and this mutual information is less than or equal to the min of F of A and F of B. Now you recall we found some inequality like this in the case of which case? City location. I mean, we actually associated the mutual information with the min, right? So recall facility location. Not only facility location and its mutual information. Okay, finally, okay, we're running out of time. Yeah. So, yeah. How is information gain monotone given that
because of submodularity, information of A comma B will be more than adding an element to A.
You're talking about the third statement, right?
Yeah.
But that is for a fixed B. It's monotone in A for a fixed B. So the statement in some sense is very much a combination of the previous two statements. So then your question is about the second or the first? Which one is your question? Because the third one follows from first and second. Okay, your question is okay. This plus this plus this equals this in some sense.
How come the first one implies this?
Oh, first one. I think no. First one doesn't imply the second. Oh, you'll have to expand on this. So I was just trying to say that as you keep growing the A, this gap is only going to increase. So I mean, there's a common thread for both of them, but first one doesn't imply the second. You'll have to go into the detailed steps of derivation. Yeah. I never implied that the first one implies the second. So I'm going to just I'm going to leave this as a little bit of extra reading for you if you want. I mean, the whole concept of differences can be thought of as gradients. So if monotonicity is saying that f of I given A is f of I union A union I minus f of A. It's called this is like the first order differences. Yeah. So I just want you to leave you with this as kind of food for thought, because we've done so much for convexity, gradient, double derivative. So think of how submodularity is basically related to second order partial derivatives, where you're looking at I comma j given A with respect to how much difference I got with respect to j and without j. So this is like a second order partial derivative. Is because of the j. Okay, so in addition to the previous two homeworks, I would say this homework relate the these differences. These are differences to partial derivatives. Okay. And what we'll do next class is now quickly move on to maximization. We'll look at algorithms for maximization on Friday. And the last two lectures, actually, even starting next class, we'll be doing lots of applications. We'll do the algorithm of maximization and just plunge into applications. So maybe almost 2.5 lectures of applications for machine learning. So I'll just make a note. Next class, I would say even less than half of next class, maximization of submodular functions. And then 2.5 lectures on application of submodular maximization in M through examples. Okay. Great. We'll end for today. Thanks.